Hi everyone, I'm Kan, and today I would like to present our work, NanoFlow, towards optimal large language model serving throughput. As we all know that the LLMs have enabled many new applications. These include AI assistants, text-to-image, creative writing, and AI coding tools. This diverse of workloads also place very surge demand towards the serving systems. For example, here, the ChatGPT is serving billions of videos per month, which places very huge pressure on the backend serving systems. At the same time, the cost of serving LLM is massive. For example, here I'm showing an H100 server, which can cost $200,000, and it's operates on 8,000 watts, which results in very high operating cost. Therefore, achieving high LLM serving throughput is a key for the cost reduction. In order to do that, let's revisit the pipeline structure of the transformer architecture. As you can see here, first I'm labeling out all the general matrix multiplications. This includes QKV generations, O projection, up, gate, and down projections. In large-scale serving, typically we use trunk to refill, which will batch the prefill tokens with decode tokens to give a large enough batch size for higher utilization. On this scenario, the weight loading is amortized, making these GMM operations compute bound. Moreover, we have this decode attention. In this case, the token will multiply with existing KV caches. Because different requests have unique KV cache, so they cannot amortize the KV cache loading cost, make decode attention still memory bound. And finally, for tensor parallel, we need to use all gather and all reduce between different operations to synchronize and aggregate. These operations are network bound. So inside the LLM serving, there are heterogeneous resource requirements. For example, we have compute bound GMMs, decode bound, memory bound decode attentions, and network bound collective communications. The question is, which resource is a key bottleneck for the LLM serving so that we need to pay extra attention to optimize? In order to answer this question, we will calculate and compare the time for the GPU to deliver each resource for the workload. So here I'm showing a figure comparing the memory time and compute time. On the x-axis, I'm showing different data sets. Some of them are from real world, some of them are synthetic data sets. On the y-axis, I'm showing different models like 80 billion, 70 billion, and MOE models. Each number in this figure illustrating the ratio of memory and compute. For example, here, 0.31 means the time to deliver memory is 31% of the time to deliver the compute, meaning that we need more time for the compute. So as you can see, because modern models use group query attention, that effectively reduce the KV cache size by a factor of 4 or 8. Most of the models and workloads are compute bound. And similarly, when we compare the network and compute, on the x-axis, I'm showing different GPUs. And on the y-axis, again, is the model. You can see that because of very high bandwidth for the data center GPUs, for example, using the NVLink, so all of these workloads are compute bound. At this step, we can make a conclusion that compute is the most constrained resource during the LLM serving. Based on this insight, we can further derive the optimal throughput when the workload is actually being compute bound. So for example, let's look at these general matrix multiplications. The embeddings will multiply with every weight element and get aggregated. So we will have 16 multiplication and 16 adds. In total, this will have 32 flops. If we further extend to the whole model perspective, then you need to do multiple general matrix multiplications, and the total number of elements for the weight is equivalent to the parameter size of the model, which we denote as P model. Similarly, in this case, you need to do P model multiplications and P model additions. This will give you in total 2 P model flops for embedding to become the output. Therefore, in terms of token throughput, you use the GPU compute divided by this 2 times P model. Note that this is a pretty constant value, so no matter what is input length, output length of your workload, as long as your workload is being compute bound, then your throughput is this constant value. For example, if we use Llama 3 70 billion model and we're running on the A100, this will give around 2,000 tokens per second per GPU. So given this insight of optimal throughput, let's check all your existing systems. Although all of the systems have made big progress towards the throughput, but still, if you compare with optimal, there's a very large gap. So the key reason behind this inefficiency is due to the sequential execution of different operations. While the compute being the most constrained resource, existing systems will sequentially go through each operations. For example, here, it first do the GMMs, and move to the decoder attention, and finally some communications. During this process, when it's actually performed the compute resource is fully utilized. However, when it's moved to the memory and network, the GPU compute utilization is very low. If you aggregate both, then you can see the end-to-end utilization is only 40%. Therefore, to increase the compute utilization is the key for filling this throughput gap. Ideally, what we want to do is to overlap different operations like this. So you want to use the GMM time to hide the execution time for the memory and network operations. However, directly doing this is infeasible because we have dependencies between different operations. For example, here, the memory operation will depend on the compute operation, and network will depend on the memory. So what NanoFlow do is to split the request batch into nano batches in order to resolve this issue. So for example, you have 1,000 tokens in the batch, and in NanoFlow, we want to split into 500 and 500. We also split the compute bound operation into half and half, do the same for the memory and network. Note that in this case, only the operations that operate on the same batch will have dependencies. For example, here, the M1 depends on C1, M2 depends on C2. But in this case, we do not have dependencies between C2 and M1 because they operate on different data, meaning that we can overlap them using pipeline. So during an execution, we first execute the first batch on the compute bound operations, and then this will move to the memory bound and network bound operation. At the same time, your second batch can start doing the compute bound operation, like this. So now when the first batch finishes network bound operation, it goes to next layer's compute bound operation, which will overlap the execution of your second batch to do the memory and network. So use this design, then you can see we have the increased end-to-end compute utilization and the shortened iteration time. However, the actual transformer is much more complex than this example where we only show 3 operations. And we do want NanoFlow to adapt to different GPU models and different models. So how to generate this schedule automatically? Let's first discuss the design space. First of all, the number of nano batches. So you can split all the operation into 2 parts like this, or you split some of the operation into 3 parts. Or you can more aggressively split everything into 3 batches. But note that because now you have smaller batch sizes, you have an overhead because your GPU utilization will go down. Similarly, you can determine the size of nano batches. For example, you can evenly split them, or you make the second one larger, or the first one larger. So you can adjust the batch size to reduce the pipeline bubbles. And thirdly is the ordering of these nano operations. This is more complex, and let's consider this scenario where we have 2 compute bound operations, compute A and compute B. In the first case, we will do a compute A first order, meaning that we do the compute A for the first batch, then for the second batch, followed by the compute B. Then we arrange the memory bound and network bound operation accordingly. However, there's a second way that we prioritize actually the first batch, meaning that we first do the compute A for the first batch, then do the compute B for the first batch. In this case, because now first batch is already finished all the compute, so you can move the memory and network forward. As you can see now, the iteration time goes down, meaning that the second one is preferred. So NanoFlow wants to make this exploration automatic. Specifically, we will do a profiling to get the execution time map from operation, batch size to the execution time. Then we will take the dependency graph to ensure the correct data flow. NanoFlow then uses this mixed integer linear programming to search for the optimal nanobatch numbers, nanobatch size, and nano operation orderings. So this search process will take around 10 minutes to finish. Here is the example of 8 billion pipeline. So originally, when you're doing the decoder attention, your compute is underutilized. But now the auto search will tell us to split everything into 2 batches, do a reordering, and finally do overlap. So the key idea here is to use the decoder attention of the first batch to overlap with the compute bound upgate and down operation of the second batch to achieve a very high compute utilization. However, this is not the full story, because if you execute 2 kernels simultaneously on 1 GPU, both of them will get slowed down. For example, it would look like this. Up and gate and decoder attention both get slower than it used to be. The design space here is you can allocate GPU resources to one of the applications more than the other, so that that operation will be faster. And for example, here, in plan A, we prioritize the up and gate, and in plan B, we prioritize the decoder attention. Again, we want to make this resource partitioning automatic. So in the second phase, what we'll do is do a more fine-grained profiling to get the execution time map from operation, batch size, and corresponding to a particular GPU resource allocation. Also, we will freeze the pipeline design in the first stage to reduce the search space. Again, we use mixed integer linear programming to find out the best resource allocation R for different operations to give the shortest iteration time. This search process will take around 30 minutes. Here is an example of what's the result for 7 billion pipelines, which is more complex. So here, for example, the up-gate down, which is one of the major GMMs during the serving, is allocated with 0.9 resources, while the network, which is not on the critical path, is only get 0.1 of the resource. All right, so here comes the evaluations. For end-to-end throughput, we compare with VLM, DeepSpeed FastGen, and TensorRT. For constant I/O throughput, we get 1.73x speed up. And for the datasets, we get 1.1x speed up, which is equivalent to around 70% of the optimal throughput, whereas optimal means 100% compute utilization. As for the latency, NanoFlow is slightly worse than existing systems at low request rate, but can handle 1.64x more requests at 200 millisecond SLO. Here, I'm showing the resource utilization during the execution. So on the left, I'm showing for a non-overlap traditional baseline that it will do the compute, do the memory, and do the network. But on the right-hand side, the NanoFlow will use 3 resources simultaneously, and most importantly, have a consistent and high utilization of the compute resource. Thanks to our auto search, we can port NanoFlow to a wide range of models, achieving 50.4 to 78.5% of the optimal throughput, surpassing existing frameworks. Moreover, we are actively building NanoFlow as a research-oriented serving engine. So we want the user to specify the operations at the model level, and the NanoFlow will handle the rest. Specifically, we'll offer operation libraries and further lower it to particular hardwares according to the auto search results. So we want to make it features a small code base, which only consider the representative models and have lower backward compatibility pressure. We will make it performance-centric that support custom kernels and automatically search for the best implementation. And finally, we want it to support heterogeneous devices, for example, CPU-GPU, GPU-GPU cooperation, and assist the pipeline design with the auto search. All right, so in conclusion, we present NanoFlow, which uses nano-batching to overlap heterogeneous operation and features the automated search and efficient runtime. NanoFlow achieves a 1.91x throughput gain and 50.4 to 78.5% of the optimal throughput. Feel free to check our paper, check out our GitHub, and contact me through email. All right, that's for my presentation, and thanks.